Okay, let's start for today's session. Welcome everyone into the last session of our hands-on practice. You already have the code files and data files and the link that I'm sharing on the screen. This link is a very good case study or a hands-on practice-based file developed by Princeton University. They usually had the PDF file. Now they converted it into a Word website so that they can update it regularly. First of all, I will go through it and then we'll come towards our code files and I will add some more things into it. First of all, it starts with what does a panel data look like. Okay, so for R, if you want to do a panel data analysis, the data should look like this. And this shape of panel data is also known as tidy data. Tidy data means each cross section has its own set and each year is repeated every time and each variable has its own column. Okay, and each number is its own event or on data value. So first column should be the cross section names and they should be repeated as long as the number of years are there. So if your data is 3 years per cross section, so then your cross section data should be repeated like this. So it is a shape of the panel data. So I will open my data file too that I have shared to you and bring it here so that I can show you that when you will be working on panel data, you make sure that your data is converted into this format so that if you have to do panel data analysis, it will work properly. The problem without it is that if you don't use this, you will eventually have to transform the data. So this is my example. My data is 2008 to 18, and for all the countries. So if you go down, there are 2025 observations and repetitive years, country name, and for each country name there are years. When you are making this data, most of the people do make a problem that they either repeat the year, like if you mistakenly write Afghanistan here instead of Alabama, Albania, what will happen is that there will be two observation where 2008 has same country, country name, so it will lead to a problem and it will not lead to a proper estimation. So while you are making it, you need to make sure this problem is not there. Okay, in my first tutorial, there is one video documentary that I attached where you talked about how to merge the data files and get it online. Use that to save your time while arranging a panel data. It will save a lot of time. Now, so this is a tentative panel data, and you need to make sure that each cross section has proper blocks. For example, the maximum numbers of years for a particular country is 10 years. It means you have to make 10 years for all the countries. Let's suppose, let me come to it. Mouse. Okay, let's suppose that the rabbit has 3 years, but cat has only 2 years. So it doesn't mean that you will not make data for cat 2020. You will write cat 2020 and leave the observation empty so that you have equal number of blocks. R does not mind having equal number of blocks, but there are other softwares that do mind, means they are sensitive to it. So you try to make a proper data so that if you are moving across softwares, you don't have any problems. So if you have equal number of years for each cross section, we call it balanced panel data. Most of the panel data analyses are designed for balanced panel data. If any one of the observation is missing, like if this row or any one of the number in this row is missing, then it means this row will be not used as an analysis. It will mean that the panel data is unbalanced, means number of years per cross sections are not equal. Now properties. Panel data has two dimensions. One is the cross section, second is here. So it is a double dimensionality data. So you have to handle the dimensionality, and Uh, then other things that panel data enables us to control individual heterogeneity means one of the dimension is cross sections, which is actually a heterogeneity. So you can handle it, and other advantage is that you can do a multi-level or hierarchical modeling in the data. So panel data has that advantage. Then there are other some issues it can handle, some it cannot. So macro panels, it can make macro panels and micro panels. We will talk about that while we are studying them. So in this website, they are making two models, a fixed effect and random effect. Fixed effect has for the two types, either cross-section fixed or time fixed. So usually in economics, we use cross-section fixed and not time fixed, and then random effects. And then what are the differences? So it starts with a fixed effect equation and a random effect equation. We will do that in our codes, and then do a Hausman test, panel Hausman test, and then it checks that if it is significant or not. So when it is significant, we say that fixed effect is better, but if it is bigger than 0.05 insignificant, we use random effect. Okay, then in the fixed effect, it is showing the types of fixed effect. It can use within, it can use random. So in the command within means fixed, random means random, pooling means pooled OLS, FD means first difference model, and between means a between model. So eViews also have this between model. Okay, so then this is the fixed effect regression results, and then these are the cross-section effects. We will do that in our results. This is the random effect model, and then simple OLS. Okay, and then it is checking that if fixed effect is better than OLS or not. This is called a redundant effects test. Okay, and this is also there in our codes. Then you can use fixed effect using dummy variables. This is called LSDV, least square dummy variable approach. So LSDV approach has one advantage, that let's suppose you are forced to do your analysis in SPSS, which is not specialized to handle panel data. Still, you can create a panel data model using LSDV method in SPSS, and then it will give you similar results. So this is the example that you should know. Then you need to see that if you need to do a time fixed effect or not. So it is a test for that. Then Hausman test is here. uh, okay, and then PLM test is for Lagrange multiplier test for time effects, and these are some extra libraries. So this data file is example is there, and it is shared in the group. Now I'll come to R. We'll start with today's data file. These are some libraries that we need to be loaded. So this is for PLM, panel linear models. Tidyverse for data management, read R for reading CSV files, and read Excel for reading Excel files. Gplots is some plots that I will use in panel data. Averaging plots, and then foreign it includes some tests. Core plot is actually correlation plot, and GG test is some descriptive stat graph. It's also called rain cloud graph. I will show you later on. Okay, so this is the first chunk. Let me set it up. So and then the working directory and the data file, and declaring data file as a panel data. So I will run the chunk together. It will load the libraries, and it will read the Excel file. It has not read yet. What has happened, that read Excel function is not, library is not there. So this is the indicator that the function is not there. So what I will do, I will add another library, read underscore read Excel, make it close, and then run it again, and data file is loaded. This was our data file that I showed you in the Excel, and this is data file declared as a panel data. So EView R knows that each row is a case of one country and one year. So it has labeled each row. In this file, it has given them numbers. In this file, it has given them identity. So this way, it can be used in making labeled graphs or some other appropriate tests. So this is the first chunk that we estimated, and you can see that I will open it up. So you can I will describe these. Next is if you need to remove missing values in the data, whole data, you can use NA omit, and then if you run it, it will remove the outliers, missing values in the data. It will remove all the rows where there are missing values. So it has not removed any because in the data file there aren't any missing values. It is prepared in a way that there are no missing values. Then df1 should remove all non-data columns, country and year. So df1.pd should be equal to df1.pd given or pipe select, and minus country means remove the country, and minus year. So in the df1.pd it will remove the first two columns and keep others. So when we run it, let's see, control enter, you can see df1.pd, the df1.pd. If you run this line, let's run from here, it says that there is one error. Why? So country does not exist. So df1.pd, country and year is not there. How do we know if there is a missing data or panel is unbalanced? So when you see your Excel file, let's say that in Afghanistan there is no value here, it's an empty, so it means it's unbalanced. So at least Afghanistan has one less observation as compared to others. So this is unbalanced panel data. So balanced panel data means at least one at all the countries have equal number of years available without any missing value. So that will become unbalanced. Software will not know that your data is unbalanced because you kept the box empty. But when you do the analysis, it will then know that Afghanistan has one less row because it has one empty value. That's why it is unbalanced. The advanced estimation models are not sensitive to unbalanced panel data, but there are some tests that require balanced panel data. So I showed you, first of all, you have to remove the missing values. If you remove the missing values, it doesn't mean that the data will become balanced. It will only mean that there are no rows that have empty values. So if you need to make sure that is strictly balanced, you have to prepare it properly in the Excel file, have a look, get the data in a way that it has no missing columns. Now if the data does not have any qualitative numbers columns, yes, stata tells us it's balanced or not, but stata is also not perfect, because if you have stata only tells data is unbalanced if your number of years per cross section are not equal. Because when you declare stata panel data in stata, you do not show the variables. Stata does not know how many variables you have. It only knows that this is country and this is year. If your years are not equal across countries, then Stata will tell it is unbalanced. Uh, and then so that's why I'm saying the advanced panel data models does not matter if the data is balanced or not. So that's why we don't need to declare data balanced or unbalanced. It's our knowledge, our information that we should know or not. Now, since the data is, let's call it without any missing value and without the alphabetical and non data column, it's a year column. We can do correlations. Control D, Control Enter. It will calculate the correlation. So if you press M, it will show you the correlation matrix if you want to copy, and then you can plot it using core plot mixed. So if I run this, it will show you a graph below. This is a graph where you can see, let me make it bigger by using this. Yes, so it's a core plot where the variable names are in diagonal and the correlation values are here. The green means y and c are positively correlated. The red means y and dummy variable are negatively correlated. I should have removed ID2, and the circles are showing the intensity. The bigger means higher correlation, higher magnitude. So this is the graph, and you can save it in high density if you run all three of them together. Okay, then you can make a graph which we call it the, let me write it here, rain cloud graph. So when you make it highlight it, and when you run it, let me run it here, run, you can see that this graph is showing one variable C, and it is showing its distribution three ways: histogram, scatter plot, and column chart. So this way, three different ways you can see how data is being distributed rather than only histogram. So it's like clouds are on the top and they are raining. That's why it's called rain cloud. So I have used the dummy of developed and underdeveloped, and to split it into two, because there are too many countries. I cannot make it across the countries because there will be too many graphs and they will not be readable. This is the second set that you can do in explaining your variables. Then in the panel data, what you can do is that you can calculate mean values across country or across year and plot it. So I will show you this example. So you can select a variable y and then compare it across countries and then plot. It will be very low. There will be too many errors shown. Then you should go down. See this. So it is showing the mean value of y across the countries. Because there are too many, it is not showing all of them. But you can see the mean value is heterogeneous across countries. So this is saying that data is different across the countries. Okay, graphically. Let's go towards if what happens if we make it across time. So when I run this, so it's showing that it is increasing gradually across time, and it is showing 184. So there are 184 countries in each cross section. Okay, so these two graphs usually used to show that your dependent variable or independent variables are not similar across time or across countries. It means you cannot use pooled OLS, which assumes that data is homogeneous across the sample. So this gives you an evidence that there is a need of advanced panel data models, not to use OLS. Let's move forward. You can make a scatter plot, and the command is that you pick df given or pipe ggplot mapping y x-axis variable, y-axis variable, color for any discrete variable, point means scatter plot, theme black and white, theme position bottom, labels title subtitle. So when you run it, it will show you a graph like this. So it is showing that that the consumption is technically positively associated with income. So C is on the y-axis and y income is on the x-axis. So you can make it better. You can add a factor here. Factor tell you can tell R that the dummy variable is a factor variable, not a continuous variable. When you run and control enter, it will make like this 0 and 1. Previously it was assuming that the dummy variable is a continuous variable. So this way you can compare your dependent and independent variables in all your analysis. Okay, next is if you want to calculate group wise mean values. So what is the method? You will compare a new data file means that will be equal to a data file pipe group by country, then filter the missing values first and then summarize my is going to mean, and if you run it, it will go in the means. It will give you the mean values for each country. So this way you can compare across the countries the mean value of each variable, and you can plot it later on. Then since we already got the means, we need to see does the means across country are constant or not, or are they not constant? So for that, the fastest way is to do an ANOVA. One way ANOVA where see dependent one variable across the country as a discrete variable or as a cross section identifier. So when you do a one way ANOVA, it will show you. Let's move forward, move it up. So it is showing that country is significant, means the mean value of the dependent variable which I used C, which is consumption, it is not equal across 183 countries. You can also do it using pairwise t-test, and it is only used if the quality that you're comparing has only two types. So when you do a pairwise t-test, it is significant here, 0.074 at 10%, which is showing that the mean value of consumption is not constant across the two values, dummy variable of developed and developing countries. So when I run them together, run this chunk together, we will have the uh, results in the bottom, all the graphs, and one of the graph is stored in the folder. Let me see if it is be stored before I convert it into a high density graph. So let me open it up. So this graph is 21 MBs, and you see how much detail it has. So you can zoom it in, high density graphs. Okay, now we go towards the next chunk. First of all, let's start with OLS. Have a look what are its results. Okay, and if and I will open my old data file from week number 3, where we discussed the cross-section regression, so that I can pick pick the heteroscopasticity command and see if it is we need to check something. So let me open it up. So if we run the OLS, where there is no identifier that the data is panel data, so it will run like as it is the cross section data, and if you do a summary, it will tell that let's show it here that both one of the variable is insignificant and one variable is significant, and see the coefficients are very small. The reason might be that your independent variables are too big, and it can be solved if you take logs. So if you generate logs and then run it, it might reduce. But is the pooled OLS suitable? We'll go here in the previous commands and find the command for heteroscopasticity. Let's see where it is and have a look if our results are heterogeneous or not. So if they are heterogeneous, we would say that the assumption that the countries are different holds, and the results that you have used are not efficient. So let me see where are the results. Heterotest. This is the command. So I will pick it up and bring it into this window and add heterotest here. It will, first of all, it will have to change the command OLS, and I will run it. It will say NCV test is not available. So let's suppose I don't know how to find it. So as an example, what I will do, I will go in the help. I will come here. Let me make it bigger. I'll come here in the help and write NCV test and search it. Let's see which library does it belong to, and that library should be loaded. So it belongs in car. So this library is car. So library car. So I will run it, and then when I come it here, this is saying that there is heteroscedasticity because it is significant. And then if I need to plot it, let's see. OLS, and when I run it, so it is showing me a plot. So you can see it here that the actual line, the purple line is not straight. It means that there is a change in the pattern which is not linear, which indicates that there is heteroscedasticity. So this is the first indicator that if you have estimated OLS and then assume that the data is homogeneous, so the study is saying that it is not homogeneous. So let's move forward. Next is library panel view. This library can show you how each cross section and observations are playing a role in the analysis. So we start with library panel view. Panel view dependent variable determined by independent variable data df and indexing your data. Indexing means that declaring which is a cross section and which is time. So I have declared it. So when I run this, control enter. Let's see. I will run it from here. So it will create a graph, and this graph might not be viewable here. I can make it using. I can make it here. Control enter. So I will zoom it up, bring it here. So this is the graph. This is showing how each country is playing a role in and in the results. So if your cross sections and time periods are homogeneous, all the blocks should have same color. They don't have similar color, which means that they are heterogeneous. And you can see that across horizontal lines, they have similar color. It means that the color is not changing mostly across time. Only there are two cases, 1, 2, and these 3, 4. There are only few cases where the color is changing across time, but there are there aren't many cases where the color is changing across time. They are all changing across country names. So it means your analysis that you're going to do here, the differences in the country matters, but not differences across time. So it means time fixed effect model is not required, or not. It would not be significant, and the cross section fixed effect would be significant. Secondly, the question that came earlier, that how do we know if it is unbalanced? So if the data is unbalanced, you will see shaded regions here that this observation is missing. So for example, let's say first country, you will have a shaded region here that Afghanistan's first observation is not there in the data. So it will tell you the treatment status, and if the data is missing, it will show you a shaded box. So this way you can this block shows you how the data is behaving in that model that you estimated. So let's close it up. I hope it is clear for you, and it will help you to determine how many observations are there, and so it has shown you 2024 observations, and if there are any missing values, it will tell you. So let's run this chunk again. So this chunk actually highlighted that that you so margins are too large. So how do we fit it? So let's let us remove this, because you have to set the chunk. So this chunk has been developed. So we have OLS results here and the graph. So we have confirmed that you cannot use OLS because there is heterogeneity, and we also confirmed that the graph treatment status is showing different results for each cross section. So let's move forward to the next chunk. It starts from here. What I should do is I will rename it fixed fixed and random effect. So first of all, the fixed effect model is FE fixed effect is equal to panel linear model, dependent variable, independent variables, data file DF, index countries, model within. We already seen from the website, within means fixed effect. So when you run it, it will load the fixed effect results, and if you want to see you can summarize, and it will show you the fixed effect results. Let's see it from here. So what does it show? It shows the formula. It is a balanced panel. It's declaring it here. So if it is not a balanced panel, it will show that it is unbalanced. How? It will say that some of the countries have different years. So it will show you minimum year and maximum years and average years. So 2024 observations, 184 cross sections. So residuals have median almost zero. So there is no biasness. If it is very far away from zero, then it shows that the results are biased because it is only because of multicollinearity. So you should avoid multicollinearity from there. So the result shows that both of the variables are significant and their R squares are R square is 3% and the adjusted R is negative. Usually adjusted R is negative when the model is over restrictive. So how you can solve it? Either you take a log on y and p or add more variables so that it can absorb. So it is the second reason for it to be negative is that its R square is very low. So either remove the restrictions or make R square bigger, then it will be solved. So let's go on the codes. Next is that you do a fixed effect FE. When you run it, it will show you. Let's see. Let me move it here. So since fixed effect model calculates intercept value for each cross section, so this command is giving you cross section value for each cross section. Each country has its own intercept value. So you can see how many are there. So this command is used for this purpose to calculate the intercept value for each cross section. Let's move forward. Then there is a PF test. So when you run it, so it's a F test for individual effects, which is also known as redundant effect test or fixed effect versus OLS. So I have not written it correctly. It is OLS. So it is significant means fixed effect is better than OLS. Then there is PLM test, panel Lagrange multiplier. So this checks that if the panel fixed effect model should include time effects also, because this model is only uh, cross-sectional fixed effect. So this is checking that this is checking, yes, checking, do we need to add time effects too? So if yes, we should use two-way fixed effect. Okay, but it is insignificant, so it means you don't need to use time fixed effect. Then this is a cross-section dependence test. So it is significant means data is cross-sectionally dependent. Then the second is other type. It is also saying that data has cross-section dependence means you had to use appropriate advanced model. Then there is a PBG test, panel Brosh Pagan test. So when you see it, it's checked for autocorrelation and it is significant means data has autocorrelation means autocorrelation can be because that you have lag effects or data is non-stationary. Mostly data non-stationary. Um, non-stationary is more likely if years per country are greater than 19. Otherwise, lag effects is a more likely reason. So for lag effects, we can use ARFE model, auto-regressive fixed effect model, where you add lag of dependent variable and you can use GMM models for that. And then if it is non-stationary, for non-stationary, you must use uh, dynamic panel data models like panel, ARDL, EDC. And now we go towards the fixed effect model. Please write in the chat if you have any questions so that I can accommodate it while I'm completing the session. So then random effect model, panel linear model, the equation, data, DF, index country here, and model random. So when you run it, it will run a random effect model. So random effect model is summary. You go to summary and then see a random effect model results. So it's showing that the data has ARF is the fixed effect model with the lags of dependent variable, autoregressive fixed effect model. The example is that you are using a lag of dependent variable, and there are many examples of that. But when you use the lag of dependent variable, you might lead to endogenous estimates. For that, people use the GMM models to solve that problem. So this is the random effect model, and the residual median is here, and the results are there, uh, and then residual the fixed effects are here. Okay. Unfortunately, in this video, the fixed effect GMM is not there because that library is not very much developed yet. I am working on that. I will try to create a tutorial when I find some appropriate coding that I can understand before I can guide somebody else. So it will come soon if I get a good library for GMM. So here you can see the adjusted R is positive now. It means that random effect model is not very restrictive and it has higher R squares also. Okay. Now let's go to the next one. So we have estimated the random effect model. Now we have seen the random effect results. Yes, so we can estimate random effect model using why the question is why we are using lag of dependent variable in the fixed effect model. We might need, according to theory, let's assume your theory says that lag of dependent variable is needed. Second reason can be if your dependent variable is very slow to change, it means it has inertia in it. In that case we add lag of dependent variable. If the data is long, you don't need to require lag of dependent variable because when you run ARDL model, it automatically adds lag of dependent variable. But if you do not add lag of dependent variable, then fixed effect model is static model. But if there is autocorrelation in the results, it means that the assumption that the model is static is wrong. Autocorrelation tells us that there is a lag effect that is present in the residuals. Uh, in other words, that your assumption that the time is not creating a role, past is not creating a role, is wrong because it so yes, if your data is stationary, you can still make it dynamic by adding lags. But if your data is non-stationary, you can make it dynamic by making ARDL model. You add lags for dependent and independent variable also. But in for stationary data means when the years are less than 19, you should prefer not to add lags for independent variables, only for dependent variable, just to avoid or absorb the autocorrelation in the residuals. And there are only two reasons that I discussed. Either the theory would be saying that you should add the lag of dependent variable, or there is a lag effect in the residual that you are going to absorb so that your results uh, do not have articulation. Yes, some studies say that if n is small and t is also n is big and t is small, then it is a wide panel data, not a long panel data. So I have shared some pictures regarding that. That what should you do in that case? You should be careful for cross-section dependence. Means the data has a spillover effects but not lag effects. So spillover effects are handled differently, and We can use GMM, yes. GMM is also a static model if you do not add lag value. If you don't add lags. So GMM is just another way to find coefficients using first or second moments. And the simple regression uses the first derivative of the function to find coefficients. So, but if you add lags and you use GMM, then GMM will also become dynamic model. So dynamicism comes from lags. You can still use GMM without dynamic and with dynamic. The advantage of GMM with lag is that GMM has an ability to handle endogeneity by adding instrumental variables, but the fixed effect model is not does not have an ability to handle endogeneity. If you want to handle endogeneity without GMM, you should use panel instrumental variable regression or panel to SLS. Okay, then you will solve the problem. So these are some model names that I discussed, but the video in the tutorial that I gave you in the Google class, the selection of models are discussed in very much detail. There are more models in that. So thank you very much for your good questions so that I am clarifying as much as possible, which is possible in this tutorial and within the relevant topics. Okay, so let's start with the next point. So this command is used if you use the declared data, you don't have to add index. So then still you can run panel data. The results will be same. Then you can summarize it. It will give same result. Then Hausman test to compare fixed and random effect model. If the results are significant, then it means that fixed effect is better than random effect. If they are insignificant, uh, we would say that uh, results are random effect is better. So these are the results for Hausman test. Then there's another model that we use for if there is heteroscopasticity. Okay, so I will discuss that and then we'll go for a break and then we'll join it again because the class will close by then. This is called feasible generalized least square. This is also within the PLM library that we have loaded. So panel linear models. So when I run this and then see uh, the results. So this is the panel feasible generalized d-square model. This model has an advantage that it is generalized version, so it means you can make the residuals robust to outliers, but you can improve the results by taking logs of the independent variables. So this model is here. So how do you make it robust? So that is discussed in the tutorial that I shared in Google class. And then if you go back, you can check for cross-section dependence again using PC panel cross-section dependence test on the model using LM method. And then you can check it using this is LM method, Pairwise LM method, and then this is Prasaran CD cross-section dependence. So if there is cross-section dependence and your data is static, then you should use let me write the names uh, Driscoll and Gray model if data is if model is static but having cross section dependence. This unfortunately this model is not there in R. I'm searching a good library which I can use or I can understand how to use, and if I find it I will do share. And if your data is uh, yes, we can also use the PCE model. So PCSE uh, panel, this is another model, panel corrected standard errors model. So PCSE. So this can be also used if there is cross-section dependence and data is static. I will give you a hint. Let's suppose you have cross-section dependence and the model that you are using and the software that you are using does not have these two models available. The best way you can do is that you can the alternative available is demean your variables before estimating. It will remove CD. So let's assume we will make it data. So df is equal to how do we do it? So df percentage, and we already calculated the we can calculate uh, let's see. So mutate and then DMC, D mean C value equal to C minus mean of C. Let's see if it is it runs. Yes. Then what I should do is I will do it for all others. DMY is equal to Y minus mean of Y, and then DMP is equal to P minus mean of P. When I run it, it will make a variable. I will copy the code for this set again. Let's run a FGLS model, name it FGLS1 using DMC, DMY, and DMP, and then check the results and check for cross-check independence. When I run this, results will be a little bit different, but the significance is same. So DMP was P was insignificant earlier too, and so there is not much difference, 1.8259 and 1.82. So the results are not that much different because you applied the D mean across all the data. Okay, now it should check is there any difference in the PCD test. Let's check it again. So I'll go up. So it is insignificant now, and this one is still significant. So in this example, one of the tests came out that the results are uh, independent. The residuals are independent, but the other is not showing. So it means that in this example there are more than one reason to solve it. So if still hetero is there, what one we can do is that we can generate a new variable that is I didn't use the I used the mean C. Yes, so technically this model will not work because it has not been successful in reducing cross-section dependence. But if yes, can we also deal it by including cross-sectional averages? Yes, you can add. How you can do it? Rather than subtracting them, you add them as a variable. Let's see. You copy it. Rather than subtract, you can make a new variable. Like I will say MC is equal to mean of C, my is equal to mean of Y. This is another method that you can use. There are two approaches to handle it. Second one is better because you add the variable as a solution. So I will copy it and come down, and rather than using the demean data, I will use MC. I will use C, M, P, and then MC, MY, MP. You have to add MC because it will help to solve the problem. So I will call it FGLS2, and then let's see how are the results. So this approach is more efficient than the first one because you have an ability to see the spillover effects. So where are the results? I didn't use. So it has not shown me these results because they are dropped. in this model. But if I use some other approach, it might add it. Let's see. First of all, let's see if it has solved the problem. Not here. Oh, let me write 2 here. Not problem solved here. Solved it here. So, so this model has worked for that. But if I use it for fixed effect, let's say, so let's say FE2, so PLM and data DF. I will copy the codes from the top. Where are the fixed effect model? Yes, so data DF and this I should copy and bring it here. Where are the results? This one. So I will copy from here till here. So when I run this model, this will show me fixed effect. Let me see what are the results. So you can see it has also not shown, because I think the algorithm in R removes the variables which are constant across cross sections. Okay, so let's see what are the results of cross independence. Still it does not work. So we have talked about few approaches to when you add the cross-section means in the model. The cross-section means tells us how a cross-section means affects the dependent variable for all countries that cross-section averages. So it means that the average value of the data across cross-sections is affecting the dependent variable across all countries. So it means this is a spillover effect. So if you search it online, one model that is called CCMG, Common Correlated Mean Group Model, that is available for dynamic data, and it is a second generation model because it absorbs the cross-section dependence. So in that documentation, I found out that when you add the cross-sectional averages, it removes it helps us measure the cross-section dependence. So let me explain it again. If you add a variable, independent variable, which is a cross-sectional average of any variable, let's assume that it is dependent variable. So you calculate cross-sectional average. Let's say, let me run it again. So what should I do? Let me add a code here. df equal to df pipe and group by country, and then pipe again, mutate, and I will call it let's name it M cross sectional average. So C cross sectional C variable that will be equal to mean of C, and then cross sectional Y variable that will be equal to mean of Y. Then you say cross sectional price variable mean of price. So this is cross-sectional average. Let me run it, and if you see in the data file, this is cross-sectional average. So it will change when the country name changes. Okay, let's come back to the code and try this variable. So I will use CC, CY, CP. So these CC, CY, CP are changing across countries, but do not change within a country. So it means it is cross-sectional invariant variable, but it is a time invariant variable, but it is a cross-sectional uh, variant. So if this variable has an effect on dependent variable, it means the country average is affecting actual data. So this is a spillover effect, means that average of a country as a data is affecting all the countries. So their averages are affecting their actual values. So that's why they call it a spillover effect. And if you want to get it in detail, you have to study the CCMG panel data model, which is available in Stata. Okay, so if I run this model, it will, let me see if it shows the results. Let me, if it is not showing, yes, it is not showing me results because it has showing plus, means the command was not complete. So it will be completed here, run, and then when I do summary, and if I show you a whole data, you can see it is not showing their cross-section average because the algorithm used in uh, the R does not show you the variables which are uh, time invariant. Okay, but if you use that approach in Stata, it will show you the variable values. I don't know, I have done promptly in front of this in the training, but I will work on it and I will show you how to see those values. When I do the cross independence, okay, so it is still showing. So the major issue is that you can use the two approaches that I have discussed here for your static data. For advanced data, you need to use second gen dynamic panel data models like CSARDL or CCMG model that you can use it here. So both of the models are available in Stata and they are currently under development for R. Now we go towards heteroscedasticity test. Okay, so let me see. Yes, for heteroscedasticity test, the library is LM test. So Brosh pagan test, and it is showing that there is heteroscedasticity for in the data. So this is also showing that you cannot use the simple OLS model. Okay, and then if your data is not normal, we have not checked it yet. So how we can check? Summary, CGWX summary, and then data file. If you run it, it will give you a mean and median. So if the mean and median are not equal, let's start with the first variable y. Y variable mean and median are not equal. For C, mean and median not equal. Price, mean, median not equal. It means data is not normal. So if data is not normal, we can use quantile regressions. So in this tutorial, I will show you how to use a quantile regression. So library contract, and then contract means RQ, and then you use the panel data. So you have to use the LSDB method. So you will use factor country. So it will become an LSDB regression when you run this and summary contract. It will show you the results. Let me open a table. So we start from the top. So let me bring it here. So y and p variables have very small coefficient value. You have to add a log to make it better. So let's do that here too, so that you can understand how to make a log. Let me come back to the output. Let me show you example here. So in this command, I have taken a log. So I will run this one, run, and I will show in the next command. So first of all, I will do the interpretation of this one. You can see it here that there are two variables and there are too many cross sections. So all the cross sections are actually the country fixed effects. So but the table was very small. The p values are shown separately as a next column. So first two columns, it is showing that my y variable is significant, but the p is not. And if you see the cross section, majority of them are significant, showing that the it will become actually the fixed effect quantile regression. Okay, now we go towards some other panel data tricks that we can use. These were the models that we were to discuss today. Now what we can do that, since there was still autocorrelation in the model, and then if you go for other diagnostics, you will notice that there is heteroscedasticity. So what we can do, here I added a scale variable. Okay, I added a scale variable for y and p, and I have taken off log for y. So when you run this, you will notice that I didn't add the cross-section identifier so that the table is smaller so that you can see the numbers. So when you see this, let me have a look. So you see the variables of L, Y, and Ly square are significant. Price is insignificant, but price square is significant at 10%. So you should take log for price too. And since I have not taken it yet in this equation, what I can do, I can just copy this command and add the log for price. So LP is equal to log for price, and LP2 is equal to log price into log price. So when you run this and change it to LP and LP2 and do a contract, all of them are significant, and the coefficients are stable. So this way you can stabilize the results. And now the next thing that we were to discuss in today's session was that if you have estimated a quadratic equation, how to plot them. So for that, I've shown you one command. First of all, you need to do a summary of your data. I will run it here. I will tell you why I needed it. And then, yes, ly variable. So first of all, you look at the coefficients. Let me bring it up. So Ly is minus 4.92 and Ly square is 0.04. So you write an equation. So here I write curve and bracket open. I am writing the equation. My coefficient is 4.92346, and for with the square it is 0.40515, and I can add the intercept if I want. That is currently it is 14.78970, and then I start with I need the starting and ending point for the curve, and in mathematics it is called domain. So if I give the domain values and the function, it will generate the range and then plot the graph. So how do I know if I should start from 5 to 12? Since the y independent variable is ly, I will go in the descriptive stat and see the minimum value is 5.6. That's why I've written 5, and the maximum is 11.6. That's why I've written 12. So when you run this equation, let's see how does it run. It will make a graph look like this. So let me make it observe. So I have plotted the quadratic function. So even though the results show, let me what you call it, let's run this, and it is already there. So even if the equation show that the results are u-shaped, because the first coefficient is negative and second coefficient is positive, but if you look at the graph, the decreasing portion is very small and the increasing portion is big, means it is positive dominated U shape. The reason is that the cutoff value is very near to the lowest value of the data or the starting value of the data. That's why the decreasing portion is not very much prominent. So this is a U-shaped curve. So this way you can plot the graphs, and if you run all of these, it will store the results in high density graphs. So I will run the whole chunk so that they are stored from here. So all the results will be estimated and the chunk will be complete. Okay, so the table will be shown here. So let's move forward to the next chunk. In the last chunk, what we are going to study, we will study how to do our unit 2 test in panel data, and there is one library that we will talk about, and where you can quickly do a panel data analysis, especially for fixed and random effect. So for panel data unit 2 test, the library is time series. When you run it, and then ADF test, it is showing that this variable is significant and means it is stationary. Okay, you can do it for other variables. So I used, if I used, I will use C. So roll enter, it is also stationary. So p value is smaller than the printed value. So it's saying that the p value is actually smaller. So it is already significant at 5%. So it will be significant at 1% also. So this way we found out that the data was stationary. That's why the results were not pointing us towards dynamic panel data model because of its stationarity, and since the R libraries are still not very much mature with respect to dynamic panel data models, that's why we didn't include any here. So inshallah in future you will see more tutorials related to dynamic panel data models, so that you can adopt it for your analysis. Now we go towards our last library. This library is called expand R, and for that there is one other library, RCPP. So RCPP is actually used when some of the commands that we are going to run are adopted from C++. So RCPP is the integration of R with C++. Okay, so RCPP, and I will load both. You have to install them. Okay, then we go towards, if you run expand R, it will open a pop-up window, and I will show you how to use it. So expand R is actually used to explore your data. So that's why it's like explore and data. Okay, so when you browse, you select the data from your folder. So I will go in week number 5, and I will explore my Excel data file. So you can pick R data file, CSV, Excel, Stata, SAS, any. Okay, and when you do it, you, since it is a panel data expanding file, so you say that my cross section identifier is country, or you can select ID. Both are same. Country is alphabetical, ID is numerical, and then you come here and my time identifier is year, and my data is balanced. I already know. Okay, so when you run it, it will start loading graphs. Let it load, and I will bring it down. So first of all, let's see. Firstly, if you want to create a subsample, because we have categorical variables, you can create a subsample if you want. Then if I don't want, you can compare it with a full sample. So I will start with full sample. If you want to group it, I can group it using DUM. Okay, and it will group it. And if you want to truncate the data to remove the outliers, okay, and then first of all it starts with the bar chart. So what does it showing? It is comparing the here variable. I should use some other variable here as a factor, and the variable that I need to display is dummy. So it is comparing the categorical variable counts across years. Okay, you can also do it across country. So it will be too big because there are too many country names. So this way you can see how many categories are changing. So it's a binomial data. Yes, there was question that if less than 10, we don't need unit 2 test. There is a reference by the Pedroni that if the data is less than 19 per year, you can assume that it is stationary. You don't need to do the unit 2 test, because you can assume the data is stationary. But still, for an evidence, you can add it, and if they are showing that they are stationary, then this is to show if there are missing values. Since our data was balanced, there is no indicator of missing values for any of the variable. There is no shaded box. Then if you want to generate any new variable like log of x, log of y, you can do it here. So I will write it there ly that is equal to log of y. So you can generate a variable within this plugin. Now when you go down, it will update after adding that y variable. So you can see that the mean and median are not equal. That is not normal. Now you can see histograms of the variables, so you can select any variable. So another example is here. You can see the y variable is not is negatively skewed, but if you see L of y, it looks more normal. So taking a log sometimes is converts the data into normal. Here dummy variable is actually 0, 1 for developed and underdeveloped. It's just a randomly created variable, but here as an example I am saying that developed and underdeveloped. Okay, so if it is developed and underdeveloped, it should not change across cross sections, but as an example, this data is there to explain changes. Now you can see the observations if you want to see, and then if you want to create a column bar chart across the qualitative variable, so I can plot across dummy. You can also plot across country, but there will be too many, and it's better not to make it. If there your countries are less, you can make them. Then there's a violent graph. Violent graph is used. It's also like a distribution plot, and uh, you can use it to see the patterns in the distribution. Here you can see the above and below are similar. You can add another category like male and female to see their differences. Since in our data there is no such categories, so that's why we don't have that luxury to show that. Next is across the time. If you want to see how the data is changing across time, so when you like it, you can just copy the image or screenshot it to use it. You can add another variable if you want with that compared to variables. The problem with that is that the units will be different. They will not cross each other. You can add the third as a third variable here. So this library is very useful if you have a panel data and you want to add descriptive stats. Then you need, if you want to show quantile wise plotting of a variable, let's see if I have a y variable. So it is showing me 5%, 25, 50, 75 and 95. So you see there are five lines of each quantile they are changing across years. Okay. Then if you want to compare two variables across time and adjusting for the dummy variable, and if I plot any variable, it will show me that how it is changing the patterns and the lines for across the dummy. Then if you want to do a correlation, it is a correlation plot. Then there's the scatter plot. If you change the dependent variable, let's say I keep my x variable ly and my dependent variable is c, and I add size with p. So bigger the dot means bigger the value of p, and the dum for color, and then there is a smoothing line. Okay, that shows that there is a exponential positive effect of ly on c. And then here there is one library that you can do a regression analysis for panel data here. Unfortunately, this library is under construction. Otherwise, it will show you the results here. But if let's see if I change them, dependent variable, I select independent variable ly and p. Let's see, I will select ly and p, two variables, and then categorical variable as a fixed effect. So I will use country, or I can use id, and the second category you can use year to make a two-way fixed effect. And if you want to subset the data, I will use the dummy. So if I select these options, when the library will be revamped, you will see the regression results here. So this library is useful to do quickly the panel data fixed effect model. Unfortunately, I only showed you the library, but when previously I did it, there was the results. But they are, I contacted the authors. They are revamping it because there's a bug that is not letting the results to show. So if I open it a browser, so this was a library that you can use to quickly see the output. Okay, and let me close it. So this was the today's session. Yes, the results are here. So since I found out the problem because I ran the expand R within a chunk. That's why the regression was not showing results. These are the results. If you run expand R outside the library, outside the chunk, it will show you the results over there. Otherwise, it is showing me here. So I have two variables, full sample for first dummy and the second dummy, subsamples, estimated OLS, both are two-way fixed effect. The observation values are these, R square and adjusted R. So this way, if you have dummy variable for development level, it will show you the results for all of them. And this is the neat table that this is the advantage of the expander library, that it will generate a neat table for you that you can show. So this was the tutorial for today for panel data. If you have any questions, you can ask here, and or you can share in the comments.